You probably interact with artificial intelligence every day without thinking much about it. It's the invisible assistant that filters the spam out of your email, estimates the value of your home on real estate websites, and recognizes your face to unlock your phone. Computers achieve these results by acting like a high-speed detective. They use math to find historical patterns in past events, and then apply those patterns to make an educated guess about what will happen next. Think of machine learning like hiring a data detective agency. Inside this agency, the algorithms are just different investigative tools hanging on the wall. The detective simply chooses the right tool depending on the specific type of case they've been hired to solve. Most cases fall into two categories. The first is called supervised learning. This is a case where the detective is handed an answer key up front. If you want them to identify pictures of cats and dogs, you first show them a giant catalog of known, labeled photos to study before they try to guess on a new, unknown image. The second category is unsupervised learning. In this case, the detective starts without any labeled examples or hints. You hand them a massive, messy pile of raw data and ask them to organize it. They have to group things together based entirely on natural similarities they find on their own. Navigating these different cases is a matter of matching the data mystery in front of you to the specific mathematical tool in the toolkit that can best decode it. The first tool in the detective's kit is the ruler. We use an algorithm called linear regression when we want to predict a specific changing number. This graph plots dots representing houses. To predict the price of a new home, the algorithm draws a straight diagonal line right through the middle of the group to show the overall trend. The algorithm finds the best fit for this ruler by measuring the empty space between its line and the actual dots on the graph. It tilts and shifts the line until those measured distances are as short as possible, which gives us the most accurate average. When we need to predict a category, like whether an email is spam or not, the detective warps the ruler, turning that straight line into an S-shaped curve. This is logistic regression, and it works by pushing data points towards the bottom or the top of the curve. Instead of giving us a house price, this S-curve calculates a percentage. It tells us the probability, say an 80% chance, that a specific email belongs in the spam folder. When the data is more scattered, the detective puts away the ruler and pulls out the map. This is an algorithm called K-nearest neighbors, or KNN. Imagine a streaming service trying to recommend a movie to you based on what you've watched. This map places you as a blank dot among other users. The algorithm simply looks at the 3 or 5 closest people to your position and assumes you will share the tastes of those immediate neighbors. Whether we are forecasting home values or suggesting your next movie, these foundational tools rely on physical distance. They measure the gaps between data points or draw basic boundaries on a graph to figure out what happens next. For medical data, where the categories are more complex, the detective uses a tool called a support vector machine, which acts like a thick wall. This graph plots patients with low risk and high risk of heart disease. Instead of just drawing a thin line between the two groups, the algorithm calculates the widest possible street between them. By maximizing that empty space, it creates a much safer buffer for predicting where a new patient will fall. Another tool is the decision tree, which sorts data by running it through a series of yes or no questions. For our medical patients, it might first ask, is the patient a smoker? Then, depending on that answer, it might ask about their blood pressure. Because a single flowchart can make a mistake, the detective uses a random forest. The algorithm builds 100 flowcharts, asks them all the same questions, and lets them vote on the final answer. Combining these simple boundaries, or letting a forest of flowcharts vote, creates incredibly accurate models that can handle the messiness of the real world. The final supervised tool is the neural network. You can think of it as a deep magnifying glass, often used for visual tasks, like teaching a computer to read handwritten numbers. A computer doesn't naturally recognize the shape of a number. It only sees the brightness of individual pixels. A neural network solves this by stacking layers of hidden detectives between the image and the final guess. As the data from the image moves through the network, the first layer of nodes looks for simple, straight lines. It passes that information to a second layer, which looks for curves and circles. These patterns move down the line until the final layer accurately identifies the number 8.
The real power here is that humans don't have to explain what a curve is. We just feed the network the pixels, and the algorithm automatically discovers these intermediate patterns to solve the case. But what happens when the detective has no answer key at all? If a company hands over a massive list of mystery customers and asks for insights, we have to switch to unsupervised learning. This is k-means clustering. The algorithm takes the messy data and drops random target centers into the map. These targets pull nearby data points into their orbit, shifting their positions until the chaos naturally settles into distinct, stable groups. Sometimes the problem is having too much information, like tracking every detail of a fish from its exact weight to the count of its teeth. To fix this, we use Principal Component Analysis, or PCA. It identifies when categories of information tell the same story. Tracking height and length is redundant, so it combines them into shape, cutting through noise without losing patterns. These tools aren't trying to predict a specific final answer. They exist to reveal the hidden structure in a dataset so that impossible mountains of data become manageable. The logic of machine learning is remarkably physical. It relies on a toolkit of clever statistical formulas that allow computers to navigate the world. By drawing lines through averages, mapping out neighborhoods, and building forests of flowcharts, we can turn raw information into meaningful predictions. Machine learning is simply the act of applying these mathematical tools to our data mysteries to find the answers hidden inside. Which of these detective tools surprised you the most? Let me know in the comments below, and thanks for watching.